This is my pleasure to welcome Professor Earl Dowell to our campus. I think Professor Dowell, for those of us who are having anything to do with aerospace engineering, he really doesn't need much of an introduction. He's one of the most respected scholars in the field. But since we have quite a few graduate students here, let me just very briefly give you some highlight. I've known Professor Dowell for a number of years, but let me just say that he is certainly the most respected, most accomplished researcher in aero elasticity of the current day. And this current day means in the last 30 years, maybe longer, okay. He graduated a few years ago, and ever since then, he has been leading many endeavors in this field. And he taught at MIT and Princeton before he moved to Duke University to become dean of the engineering school there. And he led the engineering school at Duke for a number of years. And I started my teaching career, I think, when Earl already was dean. But I can see that Duke, as many other private universities in the US, engineering is not really necessarily the largest school, but Duke has a very fine reputation, and certainly under Professor Dowell's leadership, it has really ascended a lot, okay, especially in the field that surrounds biomedical engineering, aerospace, and structural dynamics, and aeroelasticity in particular, okay. And Professor Dowell has written several books, and these are all very, very well read and used as a standard reference and textbooks. He has received probably all the prizes one can collect, okay, including the medals from the Guggenheim Foundation, from AIAA, from ASME, and so on and so forth. He is a member of the National Academy of Engineering, fellow of the AIAA, SME, and so I think there's no more prize we can give Earl, so we invite him to come to give a talk so we can learn firsthand from him. Okay. So you see, we have people still coming. Okay. Very good. I think today he's going to share with us some of his recent work in terms of nonlinear dynamics of the aerostructure. And let's welcome Professor Dowell.
It's great to be here, and I understand that the weather is a bit challenging, but now that you're here, it's better to stay and hear the talk rather than to go out in that torrential rain. So perhaps by the end of this seminar, it'll be nice and dry and sunny again, or at least not quite as hard a rain. It's a pleasure to be here. This is my first visit to your university. I've been in Hong Kong, I don't know, 3, 4, 5 times over the last 30 years. But this is the first time that I've had the pleasure of being on your campus, and it's been a delight. And I've enjoyed both the sunshine earlier and the refreshing rain at the moment. I am going to talk about the topic that you see before you on the slide, because Mark Twain, who's a famous American author, once said that when you're invited to give a talk, all things considered, it's best to choose a topic you actually know something about. So I've chosen a topic I know something about, and I hope it's a topic that not only a number of you also know quite a bit about, including Wei Shi, but also a topic that you will enjoy hearing a bit more about this afternoon. So let me begin. It's nonlinear dynamics of fluids and structures. Now that covers quite a bit. I mean, there are specialists in fluids, there are specialists in structures, there are specialists in dynamics, there are specialists in linear dynamics, and on the other hand, nonlinear dynamics. So I've lumped these all together, and I've selected topics that, for the most part, involve all elements on this slide. The other thing I've done in constructing this seminar is I've decided to give you a little bit of an introduction to several topics briefly, to give you a sense of the range and the scope of the field, but then focus on the latter part of the seminar on one topic that I hope you'll find of interest, and it's one that we've been working on quite recently. So here's the abstract. I won't ask you to read that, but there is an abstract for those of you who want one later on. But this is the bullet form of the abstract. The thought is that we have fluid forces which create structural deformation. That's not surprising. Perhaps less well known is the fact that the structural deformation can in turn change the nature of the fluid forces, and therefore there's a feedback between the fluid forcing and the structural deformation. And anytime one has a feedback system, you also have the potential for instabilities, for dynamic instabilities in particular. And those dynamic instabilities are much of what we are concerned about in pursuing these topics. Now, linear models are perfectly fine. They've been used for many years. They will continue to be used for many years. And normally they're all that you need to determine the conditions that define when the instability begins. That if I have an airplane and it flies beyond a certain critical flutter speed, a certain critical flight speed, we call it the flutter speed, and that's the jargon of the field. Then at that point, the system exhibits dynamic instabilities. There are oscillations that grow. Sometimes those oscillations are so immediately dangerous that you have the potential for losing the airplane. But the oscillations can also be encountered in a variety of other contexts. For example, in biomedical engineering, there's blood flow through arteries. There's airflow over my tongue. And if my tongue were more flexible than it is, it potentially could have a flutter instability. There is a medical condition known to exhibit that. And some people require surgery to get around that hazard. But then if you want to know not only under what conditions will the oscillations begin, but what are the actual nature of the oscillations, the amplitude, the frequency, other characteristics of the oscillations themselves. For that, we normally require a nonlinear model, and that's the subject of much of the current research in the field. If I'm working for a major airplane company, I'm probably still using linear models for the most part to design the airplane. But if I'm in the research game, I'm now trying to go beyond the context of linear models and look at nonlinear aspects as well. Because in part, even though airplanes or other aerospace vehicles are designed based on linear models, often they encounter nonlinear oscillations. And when that happens, you have two choices. One is to redesign the airplane, which is usually time-consuming and expensive, or if the oscillations are not too violent, you may choose to live with those oscillations, but then you would like to be assured that the oscillations will never be beyond a certain level where dangerous circumstances can arise. Now, the examples I'm going to talk about are the ones shown here. We're going to talk about solar sails. If you don't know anything about solar sails, not to worry, I'll say a few words about what they are. We'll talk about flapping flags. I think you all know what a flag is, except you'll see that we have a very idealized flag, and it actually is a subject that arises in a variety of contexts other than flags per se, including energy harvesting. We'll talk about buffet, which is a form of large-scale fluid oscillations, which can lead to structural motions, which can be of interest and possibly dangerous themselves. And then finally, we're going to talk quite a bit about turbulence. Turbulence is a classic subject. It's one that's been around for many years, at least over the last century or so. There have been 3 or 4 periods of time when someone declared that we understood turbulence once and for all. But a few years later, people became less optimistic. And so I should tell you that we think we now have developed a better understanding of turbulence, but we may prove to be too optimistic as well. But at least we'll tell you what we think we've learned over the last few years. So let me right away acknowledge the people who've actually done most of the work on these subjects. Again, I'm talking about things I know something about, so most of the lecture will be about work that we've done in our group at Duke. Chad Gibbs is a PhD student. He's also worked with colleagues at NASA Langley Research Center on the solar sail and solar elasticity. He's also been the person who's been working under sponsorship of the National Science Foundation on the flapping flag. Now I've defined the flapping flag. It's a cantilevered beam, which is cantilevered from its leading edge in an axial flow. And that arises in a variety of contexts, including my tongue, also including energy harvesting devices that are of interest, and some others as well. Buffet, the classic case of buffet, from my perspective, is a bluff body like a cylinder in cross flow, not in axial flow. Someone's working on axial flow. But this cylinder for the Buffett problem is in cross flow, so it's a bluff body in an aerodynamic context. And as we know, many people know, as I hope you'll studied in some course in fluid mechanics, if you've taken one or two, there can be an oscillation that occurs in the wake of that body beyond a critical flow speed for a given size cylinder and so forth. It turns out that you can make a bluff body from a streamlined object by simply placing it at a large enough angle of attack relative to the flow. So we're really interested in practical terms, for the most part, in airfoils at very large angle of attack, where high-performance aircraft sometimes find themselves. And finally, we're going to talk about turbulence. You may not recognize that in the context of this title, but I'll relate it to turbulence. This work was done by, and is continuing to be done by Jeff Thomas with some help from the Air Force. And this work on turbulence and reduced order modelings of the Navier-Stokes equations was done as a PhD student by Mike Palachevitz, who's now a postdoc at Stanford University, and continues to work on this in part, as well as some other interesting topics. So let's begin with the solar sail. I don't know if you've encountered a solar sail in your previous life or not, but this is one version of a solar sail. These are long blade-like objects. They're very thin. They're made out of mylar-type materials. There are multiple branches or blades to this object, and it rotates much like a rotorcraft or a helicopter. So think of this as a helicopter in space, but there are not aerodynamic forces on the helicopter. There are solar forces from the pressure, the solar pressure from the sun, and that is used to drive this through space for long space duration missions to planets and distant objects in the space environment. The advantage of it is that it's propulsion free, that you don't pay anything for the fuel or the fuel elements because we rely on the capacity of the sun to provide that for us. The only problem is, the challenge is that these forces are very small. Therefore, these objects, which are on the order of several hundred kilometers in length, need to be very light. Hence, they're very flexible. Hence, the solar pressure that is enough to move this light object through the space is also enough to create a structural deformation, which can lead to a change in the nature of the solar pressure, because the solar pressure force acts normal to the instantaneous surface of the deformed blade, and therefore there's a feedback opportunity, and the system can enjoy or not enjoy a dynamic instability. This simply shows a pressure chamber at NASA Langley where individual blades have been tested in a vacuum. This shows a typical ground-based simulation of this much larger object. This is on the order of a person's height, and this shows a detailed version of what the structure looks like. It's like tinfoil, right? And it's very flexible, and hence has the possibility of a dynamic instability. I won't go through this slide. This tells you how we attack the problem. Yes. Oh, yes, I'm sorry.
So is that due to the linear momentum transfer force?
The force, yes. You can think of this, these are photons just bouncing off the structure. You can, exactly.
But why do you want to have rotation?
I'm sorry?
Explain. Why do you want to?
Oh, why do I want to rotate? Oh, yes. I should tell you about that. Yeah, the reason I want this to rotate is because if it doesn't rotate, it's so flexible that it will definitely go into an instability. And so the rotation gives rise to tension in the object, yes, and stiffens the blade. Mm-hmm. Okay. In fact, thank you for asking that question, because that sets me up for the next chart. The result of doing some analysis and or tests is to develop a stability chart. And what we show here is the radiation pressure, the mean radiation pressure from the sun under typical conditions. And on this axis, we're showing the rotation rate of that device. And if the rotation rate is too small, we are in the unstable regime. as we're below the nominal solar pressure at which this device is intended to operate. Conversely, if we rotate it fast enough, we stiffen the blade from the rotation and the centrifugal acceleration that induces a tension, and we're in the stable regime in the green area. And here's the initial design. And had they designed and built that as originally intended, presumably they would have encountered a dynamic instability. But as a result of the work that we and the folks at NASA Langley have done on this, the design now has been moved over here at a higher rotational rate, so we think we're now in a safe region, and hopefully we will not encounter this dynamic stability in practice. Now, there is going to be a flight test of this in early 2016, I think. And the idea is as follows. We're going to initially be in the stable regime, and then if all is working well and NASA has sufficient courage, they're going to slow down the rotation rate and see if they can find this stability boundary. Yes.
On the size of the system.
Say again?
It should be dependent on.
Oh yes, absolutely. That's just for some typical length of the blade, and again, it's for a typical mean rotation pressure.
To the right-hand side, right?
Mm-hmm. Mm-hmm.
A large size to push to the right-hand side.
No, I'm trying to think. There are a couple of factors that are offsetting.
Basically, use centrifugal
Yeah.
force.
What happens? Yeah. What happens? These blades are so thin that the bending stiffness is very small, and it's almost entirely tension. And it turns out that actually this boundary is relatively insensitive. Because of that, this boundary is relatively insensitive to the length. There is some length effect, but it's not as much as you might think if this had primarily bending stiffness in an ordinary beam sense. So the length is not actually a major factor here. So that's the solar sail story. And where we are at the moment is we have the computations from our model. We have some ground vibration tests which basically look at the structural element by itself. So far it's proved impossible to design a ground-based total simulation experimentally because we do not have the means of creating the equivalent of the solar pressure. But people are beginning to think more seriously about how to do that because you would like not to have your first test in space where if you're wrong, you're likely to lose this vehicle. Let me turn to the flapping flag problem briefly. I know a number of you are interested in this from several perspectives. Here we have a certain flow from right to left. This red line shows the flag in two deformed configurations. Initially, it's aligned with the flow, but once we pass a critical flow velocity, the flag begins to flap. The flag, again, is something that's clamped at its leading edge. It's beam-like in terms of its structural characteristics, but it's plate-like in terms of its aerodynamic characteristics. So this is a thin sheet deforming in a uniform flow. And we need to model the fluid forces, of course, and we need to model the structural dynamics of the flag. And there are a number of things we want to think about, but one thing we want to think about is how we're going to measure the deformation, particularly of the trailing edge, and we use a laser vibrometer for that purpose. We're also going to use particle image velocimetry to look at PIV to look at the flow field. And here's the viewing window, which you'll see in a later slide in more detail. And the state of the art for the last 15, 20 years has been that we can predict with linear models the flow velocity at which the oscillations of the flag will occur, of our simple flag, where we have largely bending stiffness modeled in the structure. And we can do this with a potential flow model for those of you who studied fluid mechanics. Some people have used the Euler equations, some people have used the Navier-Stokes equations, but you basically get the same answer with any of those models for the onset flow velocity. But what we observe experimentally and what has not yet been thoroughly understood is that once we go past the critical flow velocity, this device goes into a limit cycle oscillation. Now, if you're concerned about the structural integrity of the device, you want to minimize the amplitude of the limit cycle oscillations because otherwise you may exceed the yield stress of the material or whatever. On the other hand, if you're interested in energy harvesting, where you want to take the mechanical energy of this oscillation and turn it into electrical energy, you want the oscillations to be as big as possible. And so knowing what the amplitude of those oscillations may be is important. It turns out that the amplitude experimentally is known to be comparable to the length of this device. Now you might say, well, isn't that sort of obvious? Well, not necessarily. If you have, it's one of those cases where the more experience you have in the field, the less obvious it is, in the sense that we know that if this was if the trailing edge was also clamped, we know the oscillations would be on the order of the thickness of this sheet, which is much smaller, of course. But once you remove the constraint on the trailing edge, the oscillations become much larger, which is either a good thing or bad thing, depending on the application. What has been disconcerting to the research community is that we've not been able to predict those oscillation amplitudes, even when we develop certain nonlinear models. Okay, and the question before us initially was, where is the nonlinearity coming from? Is it in the structure, or is it in the flow, or is it both? It turns out, to leap to the bottom line, it turns out we think it's primarily in the structure, but we did an experiment, another experiment, to try to determine whether that in fact was the case. This simply shows what the trailing edge is doing in terms of the laser pointing to the trailing edge and showing you one cycle of oscillation in either the top or the bottom figure. But what I wanted to show you most of all for this topic is the following picture, which is a PIV experiment, okay, showing you the flow pattern over this flapping flag. And just to orient you, the flag leading edge is, oops, went too far. The flag leading edge is here, and the trailing edge is about here. And if you look very closely, you can see a little there, the trailing edge portion of the flag is momentarily in the field of view, but primarily we're looking at the flow. And the reason we're looking at the flow is we want to know whether the flow is separated and whether viscosity is an important issue or not, and whether we have to solve the Navier-Stokes equations to determine the fluid forces, or whether we're able to use something like a potential flow model. And what we see here is that the flow is relatively benign, even though the oscillations are comparable to the length of the flag. So these oscillations are quite large compared to the chord of the flag, but the flow is actually well behaved. And so most recently we've improved the structural model, having decided that the aerodynamic model was not too bad as it was, and obtained much better agreement between our predictions and our experiment. Some of you I know are interested in Buffett, and I have a few charts. I actually have a lot of charts on Buffett, but I'm only going to show a few of them. And let me tell you what Buffett is all about. There are many words here, but I won't try to identify. Yes.
Force.
Yes.
No oscillation, flat.
Yes.
And what will be the pressure due to the flow on the
Before the flag begins to oscillate?
your force?
Yes.
Then to be not oscillate.
Yes.
Fix the boundary.
Yes.
Fix this.
Yes.
This one to be very flat.
Right.
And you have the
Right.
rule passing by.
Yes.
And then you should be able to measure the pressure on the.
Well, if the flag, everything is symmetric from an aerodynamics perspective. So if the flag is aligned with the flow, the pressure on the top and the bottom will be exactly the same. There will be no net pressure across it, and there will be no net force. Okay? And that theoretically is still a possible solution, but it's an unstable solution once you exceed this critical flow velocity. And that's when the oscillations begin. But yes, we can measure those pressures. We've not actually measured the pressures in this particular experiment. All we've done is use the PIB to look at the overall flow pattern. Okay? Okay. Now, let's talk about Buffett, yet a different topic. One we're looking at an airfoil at very high angles of attack. How high? Up to 60 degrees. So these are really high angles of attack. And that's part of the story. And as you can see, quite a few people have worked on this as a team. We've done some tests in our Duke wind tunnel. We've done some CFD modeling. We've used a harmonic balance technique, which is a technique for describing the dynamics of the system in the terms of its frequency content, as opposed to just finding a time history. And we've done some work on nonlinear reduced order modeling, which I won't tell you about because I'm going to tell you more about it later. Here's our wind tunnel and the airfoil. It's a NACA 0012, and this shows, I've forgotten what angle this is, but perhaps 45 degrees. So we're looking at mean angles of attack up to 60 degrees. This is the Reynolds number range. The Mach numbers are close to 0. And we also do an experiment whereby, although most of our experiments are done with this stationary, that is, this is a very rigid airfoil which does not move, so the structural motion is not in the picture yet. But then we can also oscillate this airfoil through a small angle and vary the oscillation amplitude and the oscillation frequency and see how that changes the flow and other characteristics. And out of all that kind of experiment, we can, in fact, find results that look like this. This is a non-dimensional frequency. I'm sorry, you have to rotate your head 90 degrees, but this is the frequency times the chord of this airfoil divided by the flow speed is the typical non-dimensional Struhel number or non-dimensional frequency plotted versus flow velocity or an equivalent Reynolds number at different angles of attack ranging from 30 degrees up to 60 degrees, and you see these characteristic lines. At these very high angles, this is very much like the von Karman vortex street behind that bluff cylinder I spoke of a moment ago. At lower angles, as we'll see in a moment, other things happen. There's another thing that can happen in this kind of experiment. Here we're plotting the amplitude of oscillation of this airfoil versus a ratio of the frequency of the oscillation of the airfoil to one of these characteristic frequencies that occur even when the airfoil does not move, the so-called Buffett frequency or vortex frequency. And what you find is when that frequency ratio is near 1, even for very small amplitudes, there's lock-in. I'll tell you what lock-in means in a moment. And then the region of lock-in expands in terms of frequency ratio as the amplitude increases. Lock-in means that although when we do not oscillate the airfoil, the flow wants to oscillate at a certain characteristic frequency, the Struhel frequency. When we oscillate the airfoil at a frequency not too far removed from that frequency, then the flow no longer oscillates at its original natural frequency, but now oscillates at the frequency at which we move the airfoil. And that's called a flow lock-in, where the flow now is locked in by the motion of the airfoil. And we can predict that as well and measure it as shown in this picture. Now, we've computed a lot of results using Navier-Stokes models of various sorts. This shows simply a depiction for various mean angles of attack ranging from 12 degrees up to 60. But perhaps more meaningfully, this shows some time histories of the lift, the non-dimensional lift on the airfoil, which we can measure through a range of pressure transducers on the airfoil. And at the lower angles of attack, such as 12 degrees, there are oscillations. There are oscillations. This is where we are in the usual stall regime of the airfoil. If I'm much below 12 degrees of angle of attack, then there are no flow oscillations at all. The flow is smooth and steady. Nothing is changing with time.
Frequency, or is in the fraction of the driving frequency?
The lock-in is to the driving frequency.
It's not a fraction.
It's not a function of it. It is the driving frequency.
It's not a rational number, 1/2.
No, it's the driving frequency.
But in principle, you should also have 1/2.
You could have other harmonics, but there's a dominant frequency, and the higher or lower harmonics usually are not immediately visible, although in a moment I'll show you some frequency content and you can see it.
The answer will be 1/2 and 1/3 and 1/5, not double.
Actually, it's the higher harmonics that you observe.
I thought it should be fractional.
Well, that's not what we see.
Okay.
That's not what we see. So, again, these are time histories at various mean angles of attack. And the important point is that the lower angles of attack, it's a chaotic or random-like oscillation. But as you get to the higher angles, such as 30 degrees, this is almost a purely periodic sinusoidal oscillation. And then as you get to yet higher degrees, it's still periodic, but now higher harmonic content is observed, okay? Yeah, right. And if you look at the frequency content, those are the time histories. Now, if I do a fast Fourier transform, then you can see what the frequency content looks like. At these lower angles, there are peaks in the frequency spectrum, but by and large, this is a broadband phenomenon. But as we get to the higher angles, there's a single dominant frequency with some second and third harmonic content. Now, one of the, I'm not sure I should tell students this at this early stage of their career for fear that you may become discouraged or cynical. But in CFD modeling, there's almost always a turbulence model of some sort in the code. And you get a different answer depending on which turbulence model you use. And so people debate which of the half-dozen extent turbulence models are the best for the purpose. And for our purposes, usually Spallert-Almirez is the best one. But you notice, here's some other popular turbulence models, and notice that while these results are somewhat similar, they're distinctly different depending on which turbulence model you use. And yeah, this is the last slide I'll show you about Buffett. Okay, you get different answers depending on which turbulence model you use in the computation. What about the comparison between computation and experiment? Well, this is for a typical case. This is for a mean angle of 40 degrees, this Reynolds number, this Mach number, this ratio of frequencies, and this degree of amplitude of oscillation of the airfoil. And here's what we're computing, and here's the experiment. And you can see that they're not perfectly in alignment. It is true that the peak-to-peak is about the same. It is also true that the dominant frequency is about the same. But this is less than perfect agreement. And as far as I know, this is the current state of the art. So let me spend the last bit of time that I have on reduced orbital modeling and the Navier-Stokes equations. All I want to do is solve the Navier-Stokes equations without the turbulence model. Why do I want to do that? Well, because I'm not sure if I really believe any answer I get if I have to use the turbulence model. I may be forced to do that because that may be the only thing I'm capable of doing at any given moment in time, but I would prefer to avoid that if I could. And the problem is that if you use the standard CFD code and you want to do calculations at any decent Reynolds number above 10,000, 100,000 and beyond, if you don't have a turbulence model, the code doesn't run. I mean, that's why people use turbulence models, not because they're great enthusiasts for turbulence models. It's what you need to make the code work. So is there some way we can avoid that? And this is an attempt to answer that question with a yes. So this is an outline of what I'm going to talk about, but I'm going to skip through this talk because this talk itself is another hour and I don't have that much time. So let me remind you that this is a subject of long-standing. Leonardo da Vinci, among others, thought about turbulence. He didn't do too many CFD calculations, but he drew some lovely, lovely pictures. So at least for, what, 500 years, we've been thinking about turbulence, seriously. All we need to do is solve a certain system of nonlinear partial differential equations. So U bar is some vector that describes the flow velocity components, the pressure and whatever of the fluid. And it's a relatively benign looking equation in abstract form because it says the first derivative of all those variables with respect to time is some nonlinear function of the flow variables themselves. And I'm going to explain as I go through this presentation why it's hard to solve that equation, harder than some other equations that we know how to solve. But let me first of all tell you how we might try to solve that equation. The standard way, a standard way, not the only way, the standard way is to use what is usually called a spectral representation. These unknowns are of some function of time in the three spatial coordinates, which I denote by a bold-faced X bar. And so I'm going to assume that I can represent this by separation of variables. That's something we all learn about at some point in a math course, right? So we're going to assume that the solution is the form of some product of time times some functions of X. And I'm going to choose these functions of X. And there are a variety of choices which I won't go through that people have used over the year. But what I'm going to try to do is come up with a better way to choose those functions. The better way meaning that I need fewer functions than I would otherwise need, and I believe the answer that I get. Okay, that's what I mean by a better set of functions. And one way I'm going to do that, in fact, the way that we have done it, is use something called proper orthogonal decomposition. I'm sorry for the missing ingredients here in terms of, but the idea is we want to determine one solution of these equations by what I'll call the old-fashioned technique. The old-fashioned technique is to use a finite difference scheme in the spatial variables and then time march. But I'm only going to do it for some set of initial conditions. But I'm only going to do that once. And the reason I'm only going to do that once is because it takes forever to compute that solution. Okay? No, it works for the nonlinear system, as I'll explain.
Then you'll have a UI and the UJ will talk.
Yes, and we're going to allow for that. Okay, we're going to do the nonlinear problem. We're not doing the linear problem. We're going to do the nonlinear problem. So we find one solution like this. And, Then we're going to minimize the difference between this assumed form and the solution we've just obtained by the old-fashioned technique. What that does, without going through the details, what that does is it determines these functions. That's the heart of the POD, or proper orthogonal decomposition method. So once we found those functions, we're going to proceed to do a projection. What we mean by a projection is the following. We're going to take this form of the solution, substitute in here, and then we're going to multiply through by each term of this sort, or say n equals some number, which will turn out to be a number like 300, 200, 100. We like it to be a number less than 10. But whatever the number is, we will take each of these functions in turn, multiply through. This is a Galerkin's method, for those of you who know about Galerkin's method. And that will determine a system of nonlinear ordinary difference equations in time for the a sub I functions. And then we're going to time march those. Now, just to give you a context, typically when we start out with some CFD code, we have on the order of tens of thousands to several million equations of motion. And we hope to replace that with a much smaller system where we're talking about at most a few hundred equations of motion as opposed to several tens of thousands or millions or more. Okay, so there's our equation again. And using the method I've just described, we're going to reduce this nonlinear partial difference equation down to a system of nonlinear ordinary difference equations and hope for the best. Hope for the best. So what happens? Well, here's an example. We've done 3 or 4 examples. I'll just show you one. This is a famous example that's used as a test case for schemes of this sort. It's a box of fluid. There's a lid on it. This is a cavity or a box. There's a lid on it, and the lid is allowed to move in some prescribed way, and the motion of that lid gives rise to turbulent flow inside the box. And we like to model that. And if you do a direct Navier-Stokes simulation of the old-fashioned sort, at this Reynolds number, this is a typical flow pattern you get, where this is the different colors are measures of different levels of intensity of vorticity in the flow. It doesn't matter what it is, but it's a flow pattern that we like to predict. And these are the functions, the spatial functions that we're going to use in our solution, the ones that we determined by the POD method, or proper orthogonal decomposition. And as you can see, we found up to 250 of these functions, and sometimes we're going to need all of them. Other times we will not, as I will describe. If you look at these patterns and you remember what the previous, well, let me show you what it looked like. Look at, that's what we're trying to model. If you look at these patterns, the first few of these functions really do a great job of modeling the exact answer. And so you would think we are in great shape because we only need a few functions to do the job. Well, it turns out to be a little more complicated than that, as I'll explain in a moment. But let me show you the good news. Here's truth. Here's the exact answer. And these are reconstructions of the exact answer using as few as 10 functions. And if you look by eye and you compare all these, we would say they're all giving us the same answer. So when we solve this problem using these functions, we would think we would get a very good answer. And the answer is yes, sort of. What we're going to show you is some global measure of the flow field. In this case, it's the total kinetic energy of the flow, summed over all the area and summed over time over some time interval of interest. We're going to show you that as a function of time. And here is truth. This is a turbulent flow, so it's a random-like, chaotic-like oscillation. And here is the answer we get using our method, using the proper orthogonal decomposition method, using only 10 of these basis functions. And sure enough, for small time, down here we start off not too badly, but quickly things go off the charts, almost literally. This is a logarithmic scale, so the answer is about 10 to the minus 3, and our approximate solution is 10 to the minus 1. We're only off by a factor of 100. That's not good enough for any application that I know of. So the question is, what has gone wrong, and how can we correct it? Yeah, I won't bother with that. The natural thing to do is just increase the number of basis functions, right? So again, truth is this gray curve, and this was the result using 10 of the basis functions, and if we go to 50, 100, and 200, indeed we approach truth. And if we have 300, which I don't have on this chart, with 300 basis functions, we're almost right on. That's the good news. So the method works in some sense. The bad news is if we do the computation to find the 300 basis functions and then do the simulation, and you look at the computation time, it's almost as much as doing it the old-fashioned way. So this is interesting, but we haven't gained anything in terms of computation time. So what can we do to improve matters? And first of all, let's understand what went wrong. Why does it take 300 basis functions? Maybe you think that that's not too bad, but I can assure you that in lots of other applications, we find that we only need 10 basis functions or less. In fact, when we made that earlier comparison, when we looked at a snapshot in time between truth and our approximate basis function representation, at one instant in time, at the small time intervals, at the early times, we were okay. But suddenly, something happened at the later time intervals that threw us off. Well, people who worked on turbulence for a long time have known that if you look at the decomposition of energy as a function of wave number, as a function of wave number, which is k, which is 1 over the wavelength, that there's a whole range of length scales and corresponding frequency scales that are important to turbulence. At the long wavelength, short wave number region, we have energy production. That's what generates the oscillations to begin with. But if we only had energy production, then presumably the flow and the mathematical solution would just go off to infinity because we're just constantly producing energy. But we need to dissipate some energy at about the same rate in order to create a balance and create a finite amplitude oscillation. But all the energy dissipation occurs at much higher frequencies, much shorter wavelengths, much higher wave numbers. That's the problem. That's why we need 300 modes, because it's the first 10 modes describe the energy production very nicely, but I need the 250th, the 300th mode, those high modes, to model the dissipation. So what are we going to do about that? Well, if we look at this chart again, we can plot on this chart these basis functions which capture the various ranges of wave number, wavelength, and implicitly the frequency. So this is why we need 250 or 300 modes, is because that's where the energy dissipation is taking place. All right, well, but now that we know what the problem is, what can we do about that? And so here's what we're going to do about it. We're going to derive a new set of basis functions, okay? We're going to derive yet a better set of basis functions. The question is how to do that. And then we're going to reformulate the problem in terms of these new basis functions. And so what we're going to do is we're going to take the basis functions we had before, these are these functions, and we're going to find some transformation set of coefficients which take us from those old basis functions to a new improved set of basis functions. But of course, the game is, how do I determine those coefficients? In words, and I won't show you the mathematics, in words what we're going to do is we're going to require that the average kinetic energy, average over all space and average over all time, is the same for the, same for the old basis functions and the new basis functions. Because it turns out that when I computed those old basis functions, among other things, I also compute that energy time average. It turns out to be the eigenvalues associated with those basis functions. So I know the exact answer, or at least a good approximation to the answer of the total kinetic energy, time average, spatially average. And I'm going to insist that the new basis functions have the correct amount of energy. But now I'm hopeful that I will only need, if I insist on that, if I have that constraint, I'm hopeful that the number of new basis functions I'll need is much fewer. And of course it is, otherwise I wouldn't be telling the story. So I won't go through the details of the mathematics. I'm going to show you some results. Again, if you use 10 of the old basis functions or 10 of the new, at a given instant in time, you get a good answer. That's not surprising. But now, here's what happens when I use the new basis functions. So I'm showing the truth, which is the gray curve. I'm showing what I'll call the standard old-fashioned basis function result. That's the dotted curve. And then I'm showing the new basis function result. That's the red curve. And with 5 modes, the old basis functions go off the chart. And I'm, depending on your standard of goodness, I'm in the ballpark, at least, with the new basis functions. And then if I go to 10 or 20, I'm getting very close. Note that the details of the time history are not replicated. You wouldn't expect that because this is a chaotic process. That's what this is. This is a nonlinear chaotic process. And the initial conditions can't be the same for 2 different models because they have different degrees of freedom. All I can expect is the root mean square results will be about the same, which they are. And if I look at the power spectra, for those of you who know what a power spectrum is, I hope that they look about the same, which they do. Okay? So now we're in business. And I think that's all I want to tell you about all this. So we've got a new approach. The method provides basis functions that are different from the usual ones. The key is that these new basis functions, in some sense, capture both the short wavelength and long wavelength modes. That's the key. And when we use those, we get a good answer with 5 to 10 basis functions, and now we're in business because the computation time associated with those is orders of magnitude less than the old-fashioned method. We could talk about future work, but I won't do that. Instead, I'll try to get out of here on a decent time interval, and thank you very much. And if there's some further questions, I'll be happy to address those.
Thank you, Earl. I'm sure Earl is waiting to take some questions?
I am. Yep.
Earl, I have a few questions.
Okay.
But just start with your solar cell.
Yes.
I think one of the most probably difficult cases how to predict when you have the say, solar burst, you have the storm.
Ah.
That is much harder.
Yes.
So how do you handle that kind of?
The answer is I don't know, but you're right. If you know they're going to design to some mean average solar radiation pressure, but they have a burst. How will the solar cell respond transiently? And I don't think they've looked at that. No, I don't. Yeah, the answer is I don't know. But that's a good question.
The next proposal.
Yeah, next proposal. There you go. We'll do a joint proposal.
Second question. Any other question from the audience? For the flag.
Yes.
Of course, for a compliant structure, that's what the flag is about.
Yes.
Right? There is a tendency to mitigate the vertical structure as a separation. But that's also a function of Reynolds number, I think.
Yes.
So if you have a case that the structure time scale and the fluid time scale, the residence time,
Yes.
then when the Reynolds number becomes say higher,
Yeah.
the capabilities of making the structure compliant to the flows tend to be less effective.
Mm-hmm.
So do you have a criterion to, because I think that's for us, it's always a competition between multiple time scales,
Yes.
right?
Yeah.
And I also feel that even for the flows, when they look benign, doesn't necessarily mean that viscosity is not important, because the flow can be highly compliant with, looks like more like potential flow, but it can also be very viscous.
Yeah, I'll give you a practical answer. The practical answer is that we've done a computation with even linear potential flow theory, plus a nonlinear structural model, and we're getting excellent agreement with the experiment. Now, there's a danger there, because maybe we could improve the theoretical model and our good agreement with the experiment might go away.
Might not be as good.
Yeah, but there's a tendency when you have a computational model that agrees with the experiment to assume that you have arrived at truth. But yes, it'd be good, even so, it would be good to do a nonlinear potential flow model or even an Navier-Stokes calculation to see if you still get the same answer.
Some sensitivity about
Yeah. No, I agree with that. The danger is that you'll destroy your good agreement with the experiment, though. So you hesitate a little bit.
Then you have a better story to tell us.
Yes.
In your reducible model,
Yes.
the selection of the basic function
Yes.
is obviously very important.
Yes.
Do you any more systematic way to select basic function?
The short answer is no. Let me repeat the question. How do you select those basis functions? And the answer, in POD, the usual way is when you calculate the basis functions, you also calculate a corresponding eigenvalue, which is usually interpreted as the amount of energy that mode contributes to the total system's energy. And so the normal way to include basis functions is to start with the one with the highest energy level, the highest eigenvalue, and just go down the list. And that's what we've done. But not in this context, but in other contexts, we've discovered that you can get false convergence. You can include 10 basis functions based on that criterion. And then if you do, and it looks like everything's great, and then you do 20 basis functions and the answer goes away, and then you use 30 and it comes back. This is a nonlinear, non-conservative system, so none of the usual theorems about convergence apply. And so we're using a rule of thumb, a seat of the pants, whatever. Conversely, what we've discovered is sometimes we want to make the computation as fast as possible. So we will do a calculation using the first 30 basis functions based on the eigenvalue criterion, but then we will go back and selectively eliminate basis functions and see if it matters. And sometimes it doesn't. That is, let's say I get what I think is real convergence after I have 30 basis functions. Sometimes I can go back and find that only the 1st, the 7th, the 13th, and the 21st are really important, and I can ignore all the rest. But unfortunately, I can only do that after the fact. I can only do that after I know the answer. But then, if I change a parameter, can I be assured that those are still the only important basis functions? The answer is no, but you might be tempted to do it anyway if you are trying to save computation time and hope that you won't get in too much trouble, and then occasionally do a 30-mode calculation to see that things are still okay. But selection of the basis functions is an open question. And I think, well, let me just stop there. It's an open question.
I think, Earl, for POD, people, when John Lumley, colleagues first revitalized some of the concepts, there was a lot of enthusiasm.
Yes.
And then when people applied the approach to turbulent boundary layer, when you get to be very close to the wall, it looks pretty okay.
Yes.
With 6, 7 modes,
Yes.
you can get away.
Yes.
Then the number of modes has to grow so fast when you get a little bit away from the wall. I think that's fundamental nature, of course, of turbulence, since you, by definition, have infinite degree of freedom almost, right?
Yeah.
I think to apply this approach to a higher Reynolds number turbulent boundary layer would be a good.
Well, we haven't quite done a turbulent boundary layer. What we have done is we've done a shear flow where we have a Reynolds number in the millions. And the good news there was that we still needed only 300 modes or basis functions using the old-fashioned POD method, and we still only needed 10 or less using the new method. So the number of modes we needed was exactly the same, or nearly the same, even though the Reynolds number was much higher, and it was a very different kind of fluid flow. And we've done one other fluid flow. So we've done 3 examples. Now, 3 examples does not prove that it's going to work for every other case known.
It's encouraging.
Yeah, but it's encouraging that it doesn't just work in this one example. It works in all 3 examples that we've tried so far.
I think I would like to suggest a case with a kind of a more disparate landscape.
Yeah.
If you have something which has,
here,
of course, it's because of the shear driven, right?
Yeah.
So it's basically circulation and the near wall effect.
Yes.
And it's not clear from the plot how the overall predictivity has been improved, because from the fine structure it's hard to tell.
Yeah.
I think it'd be good to have a little bit more with the.
You got another proposal. That's good.
I'm not making a proposal.
I hope you know somebody with money who's going to fund this proposal.
That's right. But I do want to defend the turbulence model. This is something closer to my study. For our students, first of all, for time-dependent mean flow, turbulent flow, it is of course notoriously difficult to use turbulence model.
Yeah.
However, people have been doing that. I think one thing fundamental is it is hard to not to show some kind of a grid sensitivity stuff.
Yeah.
Right. For this kind of flow, naturally, I would expect that when you sufficiently refine the grid, the difference will become smaller. I think there is always this resolution versus modeling effect. Right. The second thing is, of course, then when the flow becomes three-dimensional, it's hard to use a 2D model to replicate certain features.
That's right.
So with the computer we have today, I think this some things can be mitigated a little bit better. Okay? So, but on the other hand, certainly for turbulence model, it's always.
And we use turbulence models too. I mean, we do other work, and sometimes we use a turbulence model and hope for the best. Yeah. Yes, sir.
So suppose you fix the size of the U, okay, just force U to be limited, bounded by certain value.
Yes.
So you still have turbulence.
For fixed switch.
So that's a Navier-Stokes equation. Right?
Yeah, and why would I fix it?
U will be bounded by certain value.
You're talking about the flow velocity?
That's right.
Well, in this particular example, based on a Reynolds number based on the velocity of that upper lid and the usual viscosity and the length or the size of the box, for a Reynolds number of about 10,000, that's when the laminar flow becomes unstable, as predicted by a direct Navier-Stokes calculation. And if you don't know if you read the chart in the fine print, but we were doing these calculations at Reynolds numbers around 30,000. So we were way into the, by our standards, way into the turbulent flow regime, way past the point of instability for the laminar flow. But by the way, one of the things you want to do is you want to only do these calculations as infrequently as possible. So one of the big issues is if I do if I construct a reduced order model at one Reynolds number, will it still work at a different Reynolds number? And if the answer is no, then this method, as wonderful as it is much less attractive and much less practical. And all we've shown so far is that if we do a calculation of a Reynolds number of 30,000 and construct those basis functions, it still works pretty well at 40,000. But I doubt if it's going to work very well at 1,000,000, right? I mean, there's some, if I go away far enough from the Reynolds number where I constructed the basis functions, then I probably have to do another construction at that other range of Reynolds number. Yeah, yeah.
Law is directly proportional to Reynolds number times power, right?
Yeah, yeah. The hope is, of course, if you go high enough in Reynolds number, eventually you're going to asymptote out, but we don't know that yet. Yeah.
Other questions? If not, let's thank the speaker. It's a very interesting sample with the different topics.
Thank you. Thank you.